All right, so hello, welcome back, everyone. So as always, I'm gonna wait a few seconds for Learn to get everybody into the room. All right, so people are popping in. Okay, so I'll start with some technical announcements. So, I mean, one, I noticed that the video quality in Monday's lecture was not too good. So I've been trying to improve things, changing the lighting, the camera, trying to get the camera closer to the whiteboard. So, I have some other ideas for improving things, but let's try and see how things go today, and hopefully it'll be better. If not, I'll try and improve the video quality in some other ways. In terms of groups forming, so approximately half of you are now in groups, so that's good. And so, you know, I'm just going to harp on this and remind you, assignment 0. I really want you in groups by Monday, so that you can start looking at the assignment and working on the project. So I know it's hard to find group members because everything is remote, but please use the Teams channel or the Piazza chat to try to get yourself into a group, you know, sooner rather than later. Okay, and on Monday, you know, whoever's not in a group, I'll start contacting you and trying to force you into a group. Okay, and so as always, or as before, if there's questions, you know, feel free to use the chat to ask questions anytime, and you know, just say question in the chat, and then you can use your microphone to ask a question verbally if you wish. Okay, so we can get started. So as I mentioned on Monday, sort of the first half of our compiler is going to be the analysis phase. And the idea is that we're trying to determine you know, what the program means, and then the second half, the synthesis phase, is going to generate the target program with the same meaning. But aside from figuring out what the program means, the first question we want to answer is the input a valid program? Okay, and I mean, here by valid program, you know, how do we know what's valid? Well, it's not that we're trying to look for bugs in the program necessarily, but what's valid is whatever the spec says is valid, right? So you get your Java language spec, and it tells you all the rules of valid programs. I'll stand over here so you can see. Okay, but really, for the rest of the compiler, what's important is we want to determine the meaning of the program so that we can generate code for it. But that's, you know, and sometimes I sort of overemphasize valid programs, right? In some sense, the marmoset tests will mostly check whether you're detecting valid and invalid programs. But that's important because the spec, you know, the spec also tells you the meaning of programs, but the meaning of programs is only defined for valid programs, right? So, you know, to give a crazy example, if I write a program that, you know, prints the value of some variable and that variable hasn't even been declared, you know, then what is that program supposed to do, right? So that would be an invalid program, and there the spec doesn't even give a meaning to valid programs. Okay, so, you know, a lot of it is going to focus on checking validity, but that's deeply connected to the meanings of programs. Okay, so whenever you're writing a compiler, you can just use your programming language and write some code. But whenever possible, it's nice to be able to use formalisms, to use some theory to make the job of writing the compiler easier, right? So whenever we can, we're going to try and use theory. And so for the early parts of the analysis phase, we're going to use topics from formal languages. Okay, so we're going to use things like regular languages and DFAs, deterministic finite automata, and context-free languages and context-free grammars. So those are all topics from the theory of formal languages. I hope most of you, I wish all of you had taken CS444, which is a course that's all about the theory of formal languages. So I'm going to not repeat things from there and go through these things quickly. But if you haven't taken that course, you're really missing out. You should consider going back and taking CS444. It's not required for some of the programs, but it's still a really valuable course. Okay, but we're just going to use that theory. So all I'm going to do here is take some terminology from the theory of formal languages that we're going to use for the next few lectures. And so the three key terms that I'm going to use are an alphabet. And usually we use the letter sigma to stand for an alphabet. And so for us, the alphabet is going to be a finite set of symbols. Okay, and so at different phases of analysis, we're going to use different alphabets, and we'll see those along the way. Then once you've defined an alphabet, a word, and I'm going to usually use W for words. So a word W is a sequence, and for us, it's going to be a finite sequence. And I'll do seek for sequence of symbols from the alphabet. Okay. Once we've defined alphabets and words, languages are going to be, and so I'll use L, capital L, for languages. So languages are going to be sets of words. Okay. Hopefully you've seen those definitions, if not in CS444, maybe in CS441. Okay, so just so we have some terminology for that. And then in terms of the analysis phase of the compiler, we're going to start with scanning, or a fancier name for that is lexical analysis. And let me do that here. So lexical analysis or scanning. And so, one thing you could do to implement lexical analysis would be to, look at the Java spec, and it's in chapter 3 of the Java spec. Yep, that's chapter 3. And so it gives you an English description of the lexical analysis that you need to do for Java, and you just take that description and translate it into your favorite programming language. Okay, but we're going to try and leverage some of the theory a bit more. So what we want to do in lexical analysis is take a program that's an input as a sequence of characters and split it up into a sequence of tokens. Okay, so, as an example, if I have, say, a program that's like int main, int a, I don't know, return 42. Let's say a plus 42. Right, so if that's part of my Java program, what I want to do is split it up into, informally we would call them words. Formally we would call them tokens, and basically take that sequence of characters and break it up into a sequence of these bigger pieces that we can then do more with. Okay, and part of the reason why we do this is that for the parser, which is going to come after the scanner, it's easier to work with tokens, with these characters grouped into words or tokens. Is anybody here? I just get nervous when I see no comments at all in the chat. So I don't know. It does say people are here. Okay, yes, people are here. Thank you. Okay, yay. And of course, if you have questions, you can ask them. If you don't have questions, that's fine too. But I'm glad. Okay, there's tons of people here. All right. Sorry. I mean, this whole online teaching thing. I think I'll never fully get used to it, but I'm still kind of getting used to it. In real life, I'd be able to see all of your faces, and I really miss being able to see all of your faces. But anyway, okay. So we want to split the input into tokens, and so how do we do that? And so just to throw out some words here. So we're going to use the maximal munch algorithm, and I'll talk about that algorithm, a little bit later. But yeah. So if you remember the maximal munch algorithm from CS444, great. If not, well, we're going to review it quickly because we've looked at it in CS444. But for many of you, that might have been a long time ago. Okay, and if for this algorithm, we're going to use deterministic finite automata to specify the language or the set of valid tokens. So we're going to create a DFA that says, int is a valid token, main is a valid token, but maybe close parenthesis, open brace is not a valid token. That pair of symbols is not a valid token, but each individual symbol is a valid token. So the DFA is where we use the theory to specify what valid tokens are, and then the algorithm is going to use that DFA to do the scanning to find the tokens. All right, I'm not going to go into the details of DFAs because hopefully you've seen them in 241 and 360. If not, if these concepts like DFAs and NFAs and regular expressions are totally new to you, I would suggest that you look at some of the textbooks that I mentioned on Monday, just to get some background on them, or even just looking online. There are fairly well-known concepts, so there's a lot of material about them, definitely in every compiler book, but also online. Okay, so I'm assuming you know what a DFA is, but how do we get a DFA to specify the valid tokens, right? Where do we get this DFA? to use for our scanner? Well, so one option, and it's an option that I sort of advocate for at least in CS444. One option is to just draw the DFA directly. Get out a piece of paper and start drawing bubble diagrams for your DFA and design your scanner directly as a DFA. So design directly. But another way that this is commonly done is to use a tool. So a tool that generates the DFA. And I'm going to say, well, so the idea is you can get, okay. So the idea is that you specify your language of valid tokens using a regular expression or using a set of regular expressions for the various kinds of tokens that you have. And then you give that regular expression to a tool. And one such tool or a very popular, very well-known such tool is called Lex. And Lex is sort of the grand ancestor of all of these kinds of scanner generation tools. And so, Lex was around many years ago, and then there have been, many re-implementations and variations on it. Typically, they often have Lex as part of their name. So, you've got like JLex and Flex and, ML Lex and so on. So Lex is sort of the traditional name for this kind of tool. But the idea is that you write a specification of the valid tokens in your language as a set of regular expressions, and then this tool automatically generates the DFA for your maximal munch scanner. So then you implement your maximal munch scanner and you run it on that DFA to scan your program. Okay, so we've done scanning in CS444. What I want to talk about here is how Lex works, right? Because it's a common tool used to generate scanners, how does it actually work? How does it convert a regular expression or a set of regular expressions to a DFA? For your project, how you design your scanner is up to you. So you could ignore all of the formal language stuff and just write a bunch of code for your scanner. Some compilers do that, and that works as well. Or you could design a DFA directly and implement the maximal munch algorithm with your DFA. Or you could implement yourself like a baby version of Lex, following the lectures. This is up to you how you decide to design your scanner. The only rule is I don't want you to go and use a Lex that's already out there, right? So this is a popular tool. There's versions of them for many languages. I want you to, if you're going to use a tool like Lex, you need to write that tool yourself for the assignment, okay? Because I don't want you to just use the tool. I want you to understand what it does. Or at least if you're going to instead design the DFA directly, then you're kind of doing by hand what Lex would do for you. So that's good enough in terms of understanding what Lex does. So what do production compilers typically do, considering things like speed and error handling? And so it's a split. So some compilers will use a tool. One of the benefits or one of the nice things about DFAs is that scanning with a DFA is very fast. In theory, you could write a scanner that works directly with regular expressions. But sort of the reason that you would use a tool to go to a DFA is that it's a very efficient way of scanning. And many implementations of LEX and LEX-like tools have various features for error handling and reporting error messages and so on. So many compilers do use a tool to generate the scanner. Many other compilers also, just write a scanner in whatever language the compiler is implemented in. So it's a pretty even split. The same goes for parsers. So later on, we're going to look at parsing. And again, many compilers use a parser generated from a grammar, and many other compilers have a handwritten parser. So it's there's no clear winner. The benefit of using a formal language and then tools that build from the formal language is that the formal language gives you a specification, right? And you'll see that if you're reading chapter 3 of the Java language spec, it's terrible reading, right? Like you'll be tearing your hair out, reading all of the spec, but chapter 3 specifically, and you'll be thinking, hey, why didn't they just give us a DFA? Like that would have been so much more practical, right? Both unambiguous and it's half your implementation already there, right? So if instead of all that English language text, they had just given you a DFA, well, then you'd have a nice, clear specification. So it's a trade-off. Okay, so how do we build this LEX? So I say we're going from a regular expression to a DFA, but actually we're going to go in 2 steps. We're going to go from a regular expression to a non-deterministic finite automaton, and then from the NFA to the DFA. Okay, so there's going to be 2 steps, so we'll look at the first step first. All right, so I'm going to erase this off. Okay, and so regular expressions. So, what's a regular expression? Well, hopefully this is review, but so one kind of regular expression is 0, and the meaning of that regular expression, so I'll say L, the language that regular expression represents over here, it represents the empty set of words. Okay, and so 0 is one possible regular expression. If I have A as some symbol in my alphabet, so I'll say A is a symbol in my alphabet. So any symbol in my alphabet on its own is also a regular expression, and the language that that regular expression represents is a language with exactly one word in it. So remember, language is a set of words. This is a set that has one word in it. That was a set that had 0 words in it. So a set that has one word in it, that word has one symbol in the word. So word is a sequence of symbols. That symbol is A, and that's that symbol from the alphabet. Okay, so A, for any symbol A in the alphabet, that's a valid regular expression. And then, the special symbol epsilon, that's not an alphabet symbol, is also a valid regular expression. And it represents a set of words. It's a set that has one word in it, but that word is the empty word. And the empty word, is hard to see because it doesn't have any symbols. So we often write epsilon as a representation of the empty word. So sort of the difference here is that here we have a set with 0 words in it. Here we have a set with 1 word in the set, and that 1 word is a word with 0 symbols in the sequence of symbols that make up the word. Okay, so those are the sort of the trivial cases of regular expressions. So 0, A, and epsilon are all valid regular expressions. But now if I have 2 regular expressions, E1 and E2, then I can write those 2 regular expressions one after the other, and the result is also a regular expression. So this is how I can, generate bigger regular expressions out of smaller ones. And the meaning of this regular expression is a set that contains all words x, y. So all words, all sequences that can be split up into subsequences x and y, such that x is in the language of E1 and y is in the language of E2. Okay? So, any word that I can chop in half and, somewhere, and the first half is in the set specified by E1, and the second half is in the set specified by E2. All right, so I start building up bigger regular expressions out of smaller ones, and yeah. So another way I can build a bigger regular expression is with disjunction or, and it's usually written as a vertical bar. And so the meaning of this regular expression is I take the language of E1, that's a set of words, and the language of E2, that's a set of words as well, and I take the union of those 2 sets, and that becomes the meaning of this regular expression over here. And finally, there's one more constructor, or one more kind of regular expression, and that's the Kleene star. And so I can take a regular expression, put a star on it, and then its meaning is so informally you could say it's any number of repetitions of E, including 0. Okay, so the meaning of E star is the language that you would get with this infinite union, right? This goes on forever, but of either epsilon, the empty word, or one E or 2 E's or 3 E's or any number of E's. Okay, and one sort of a common confusion, people often ask if I have a word that is matched by this regular expression, do each of these instances of E have to match the same substring, right? So, if let's say E was the regular expression A or B, so I had A or B star, well, then the answer is that each instance of this E can match a different word. So, ABA would be in A or B star. It doesn't have to only be a string of all A's or a string of all B's. The A's and B's can alternate. Okay, so regular expressions, this is pretty much all I'll tell you about regular expressions. So stop me if there's questions about regular expressions here, because this is all I'll tell you because you've hopefully seen them before, but this is your last chance to ask questions before if you do have questions about regular expressions. Okay? No? All right. Okay, so now, before I go and erase this, so the idea is we're going to have a file that specifies regular expressions for our tokens, we want to turn that into a DFA, but we're going to go to an NFA first. So, how do we go from regular expressions to NFAs? And sorry, one last thing that I forgot is, nobody asked this, but you can have a question like, why? Why do we have a tool like Lex? Why do we write things as regular expressions and then generate the DFA when you could just draw the DFA in the first place? And, typically the reason is that regular expressions are easy to write down, right? A regular expression looks like this, and, you have a vertical bar and a star on your keyboard. And so, they're easy to type with your keyboard, and so you can put them in a file. Whereas a DFA, it's hard to type it. It's a bubble diagram, right. So it's hard to type it. It's hard to edit it. If you put a diagram in Git, it would be hard to maintain diffs for it. Also, in some cases, you can have fairly small regular expressions that end up generating much larger DFAs. Okay, so let's say somebody has gone and written a set of regular expressions for the various kinds of tokens in Java or in Juice or whatever language. And now we want to take that file and translate those regular expressions into an NFA or a DFA. Okay, and so the way that we're going to do this is we're going to recurse into the structure of the regular expression. So basically, for each of these kinds of cases, I'm going to create an NFA that recognizes exactly the set of words or the language represented by that regular expression. Okay, so I don't know. If I could see you in person, I would say I would have you guys help me. Hey, how do I draw an NFA for the empty language, right? Well, it's kind of hard when I can't see faces in person, so I'll just do it, right? So an NFA for the empty language. Well, I'm just going to have have NFAs over here. So I'm just going to have a start state, and it's a non-accepting state. So the idea is it's for the empty language, and there are no words in the empty language. Okay, so this, you're going to go in the start state. There's no transitions out, so if you see any symbols, you're going to crash immediately. And if you see the empty word, well, you're going to be in this state, and it's a non-accepting state. So we're going to reject all words. So here's an NFA for the empty language. Okay, and I've got a question. Why would we convert all the way to a DFA instead of just using an NFA directly? Okay, yeah, so you could implement your scanner in terms of, so the maximal munch algorithm, it's sort of traditionally implemented in terms of a DFA. I mentioned you could implement one in terms of regular expressions directly. It would just be quite inefficient. And an NFA is sort of the same argument. So you could convert the regular expressions to an NFA, then run maximal munch on the NFA. The issue is if I want to implement maximal munch on an NFA, or if I want to implement any algorithm on an NFA, at each stage of scanning, I need to maintain data structures of sets of NFA states. And maintaining a set of states, that data structure, manipulating that data structure is more expensive than just being in a single state at a time, like in a DFA. Okay, so again, it's a matter of efficiency, also simplicity, right? If you want to do maximal munch on an NFA, you need to implement that set of states data structure, whereas with a DFA, you can label each state with just an integer, and then you're just going from one integer to another. So the data structures are simpler. Okay. So in converting an NFA to a DFA, are we not doing the same thing, just abstracted away? That's a great question, and yes, I should explain this, right? So we're going from a regular expression to an NFA to a DFA, and the important thing that I should have mentioned and forgot is you do this once, right? So it's usually it's the part of the build process of your compiler. So when you go to compile your compiler, that's when you take your regular expressions, you run Lex or whatever your version of Lex is, you do that conversion, and you put the DFA in the compiled code of your compiler. And that way, every time your compiler compiles, your compiler then goes to compile many programs. Each time it's using the DFA. So you only do this step once when you're building your compiler, and then the compiler can be fast for every time it runs. Okay, so this step can be sort of expensive, right? It can take a few seconds, and that's something that you don't want to. That's overhead that you don't want to have for every single file that your compiler then goes and compiles. The same applies to parsers, which we're going to look at later, and there it's even more of an issue. Typically, generating the parser is we're going to generate a DFA for the parser, and that is even more expensive than for the scanner. So again, it's something that you want to do once when you're compiling your compiler, and then when your compiler is running, it's running a DFA, so it can be very fast. All right, good. Thank you for questions. I'm happy when I get questions. So, yes. Okay, so right. So we need an NFA that's going to recognize the word with the language with one word in it, and that word is just A. So, if you remember your NFAs and DFAs, there's my NFA. It's also a DFA. So I've got my start state. If I get the empty string, I'm in the start state. It's a non-accepting state. If I see A, then I'm in an accepting state. So I'm happy. If I see anything more than A, there's no transitions out, so it's going to crash, right? So, there's my NFA for that. And then for the empty string, it's like the one for 0, but my start state is now an accepting state. So, as soon as I'm in the start state, I'm going to accept the empty string. But if I have any non-empty string, it's going to crash because there's no transitions out. Okay, so those are the base cases, and now the interesting cases are going to be these three. And I guess so far I only have DFAs, right? So then it's for the interesting cases that I'm going to need NFAs. Okay, so for this case, for E1, E2, I'm going to assume that, or I'm going to recursively construct NFAs for E1 and E2, right? So if I'm implementing this, I will make a recursive call to my a regular expression to NFA builder, and I'm going to say, hey, give me an NFA for E1, give me an NFA for E2, and then, sort of the idea is I'm going to connect up those NFAs together, right? So each of these NFAs inside it is going to have a start state, and it's going to have some number of accepting states. So I'm just going to draw them here, and then here I have a start state and some number of accepting states. So I'm drawing 2, but you could have 0 or more. Okay, and so this is what I get from the recursive call. And so now the question is, how do I take these two NFAs and hook them up together to give me an NFA for E1, E2? Well, okay, so for your start state for the new NFA, that's going to be the start state of E1, because when you start looking at a word, you want to just see if a prefix of the word matches E1. Once you get to a prefix of the word that is matched by E1, E1 is going to end up in an accepting state. So from all of these accepting states, what I'm going to do is create a new state in here and put epsilon transitions to there. And then from that state, I'm going to go with an epsilon transition to the start state. Okay, so the idea is that if you're in any of the accepting states of E1, you can take these epsilon transitions to go here and then to the start state of E2. Okay, so if I have a word where I run E1 and then at some point I'm in an accepting state, I can switch over to E2. And then if E2 ends up in an accepting state, so the accepting states of the overall NFA become the accepting states of E2. Oh dear. Sorry, hopefully that didn't block things. Okay, so why add this middle state? Yeah, so and I'm not quite sure whether that's is that actually necessary? Let's see. So the reason for it is, in case there are inside here, in case there's other epsilon transitions out to other states, you don't want things to get muddled up, or possibly like other transitions back from various states. But I think strictly speaking, it's not necessary. You could identify the start state in E2 and just make these transitions go directly to the start state of E2. I think it's just a matter of keeping things simpler and cleaner to introduce that extra state so that all these transitions go to one place and it's independent of the internals of E2. Okay. Would we also have to make the accepting states of E1 not be accepting anymore? That's right. So the accepting states of E1 should no longer be accepting. So I guess in the diagram, I guess I'm using red for the new NFA. I guess if you want, you can put X's here to say these are no longer accepting, right? If I was writing this out formally, I would say that the accepting states are only the accepting states of E2. Okay, good. Thank you for questions. Are there more questions? All right. So, okay. So this is the basic idea that we recursively create NFAs for E1 and E2, and then we, combine them together in the right way to end up with an NFA for the overall regular expression. And we're going to do, essentially the same thing for the other two kinds of regular expressions as well. Okay. So for the OR, again, I'm going to recurse, and I'm going to ask for an NFA for E1. Okay, and an NFA for E2. Do it like this. Okay, and then, then the question is, how do we combine them? And so here, I am going to introduce a new start state. And I'm going to have epsilon transitions going to the two old start states. Right, so the idea is the NFA, as a first thing, it's going to decide, am I non-deterministically, is the word a word in E1 or is it a word in E2? Right? So I'm going to go to either of these, and then again, I could make all of the accepting states of both of these be the accepting states. So make these be the accepting states. Alternatively, you could create a single new accepting states and just add epsilon transitions to that single new accepting state. So that would be another way of, an equivalent way of doing it. That then you end up with fewer accepting states, but more epsilon transitions. Okay, so yeah, and so this is gonna accept a word if and only if at least one of these two NFAs accepted it. Okay, and then finally, so again, if there's questions, okay, I think you know by now if there's questions you can ask questions. All right. So then we need to do E star. So we need to build an NFA for E star. So again, we're going to recurse, and we're going to go and create an NFA for E, and it's going to have a start state and accepting states. Okay, and so here, so what do we want to do? Well, I'm going to, I'm going to go switch to red. So I'm going to create a new start state that I'm going to designate to be an accepting state because, remember E star is supposed to match the empty string as well, or 0 iterations of E is one possible number of iterations. And then I'm going to put an epsilon transition, into that NFA, and so now what happens? Well, if my word is matched by one iteration of E, well then I'm going to take the epsilon transition here. The NFA is going to run on E and end up in an accepting state. And then to allow more than one iteration of E, I want to put epsilon transitions from all the accepting states to this newly created start state that I created, right? And so then, this can be my only accepting state, right? These existing accepting states, I can either keep them accepting, so that if my E NFA matches the string, then we'll be in an accepting state, or I could make them non-accepting, but I can still just always take the epsilon transition over to this accepting state. Okay. So then I have an NFA for E star. I think here it's more important to create really a new start state because I need the start state to be an accepting state. And it could be that inside the NFA for E, that the original start state was a non-accepting state. And yes, it's the start state, but it could also be a state that there's other transitions to, that somewhere in the middle of recognizing a word, you end up going to that start state. And if I take a state that was non-accepting before, then it might, and make it accepting, then I might start matching extra words. So that's where it's important to create a new state. I think here it's not necessary. I just do it anyway just to be safe, right? It's kind of always safer to create new states than to try to mess around with existing states. And you might worry about efficiency, like if I create new states, but that's actually not an issue because when I go to turn the NFA into a DFA, those extra states are going to go away. If I've got lots of extra states with epsilon transitions, those will go away during the conversion from an NFA to a DFA. Okay, so now on to that conversion, if I can find the right page here. So before I go to converting NFAs to DFAs, are there any more questions about converting regular expressions to NFAs? Okay, if not, I'm going to erase all this. The last call. All right. Okay, so we have, out of any regular expression, we can create an NFA by recursing on the regular expression and applying these sort of NFA transformations, I guess you could call them. Okay, so from my regular expression, I now have an NFA. And now I'm going to do a conversion of the NFA to a DFA. And this is an important transformation. It's important because it comes up not only in the parser, not only in the scanner, but also in the parser. Okay, so this is kind of a generally useful algorithm that comes up in a number of places. So, make sure you understand this algorithm well, because you're going to need it later. And I'm sure it comes up in places outside of compilers as well. But it, we see it in at least 2 places in our compiler. Okay, so for this conversion, I've been drawing NFAs with these bubble diagrams, but if you've seen NFAs or DFAs in any other course, you might remember that formally they are 5 tuples, right? And so we have a tuple where we list out the alphabet, right? The finite set of alphabet symbols. We have a set of states Q. We have a start state Q0, a set of accepting states A, and a transition function delta. Okay, and so, hopefully you remember this part from, oh dear. Oh, your mic, I thought my mic was muted. Okay, so somebody has a unmuted mic. Yeah. Jashan, can you mute your mic? I don't know if okay, or I can mute you. Apparently, Learn gives me powers. All right. I also have my kids running around and making noise in the background. I will tell them to be quieter next time, but I don't know if that was, if you could hear that, but anyway, all right. Okay, so where was I? Right, so NFA, formally it's this 5 tuple, and these are sets and functions and so on, right? So, hopefully you've seen that formal definition in various previous courses. And just as a reminder, they both NFAs and DFAs kind of look the same. The only difference is that in a DFA, the transition function delta, it's a function from pairs of states and alphabet symbols. So if I, for every pair of state and alphabet symbol, the function returns me a new state. And in an NFA, I again have a function that takes a state and an alphabet symbol, but this time the output of that function, the return value, is a set of states. And so sort of a mathy notation for a function that returns a set of states is 2 to the power of q. But really, that's just a way of saying a set of states. Okay, so the only difference is that for a DFA, the transition function returns one state. For an NFA, it returns a set of states. Okay, and so, well, we have an NFA and we want to create a DFA out of it. So, we can sort of think of an intermediate step of removing the epsilon transitions, or you can kind of roll that step into the main step. But either way, it's useful to define the idea of an epsilon closure, right? So doesn't the NFA also accept epsilon in its state transition function? Yes. So so it depends on how exactly you formalize it. So you could, but yes, I think the way that we've been drawing them, we should allow epsilon here as well. So you're right. So I'm going to say sigma union. Yeah, okay. Now it's going to get messy here. So union epsilon. Right? So you want to allow transitions on epsilon. That's 2 to the q, right? And and so sometimes when people talk about the theory of NFAs, they don't include the epsilon, because you can take an NFA and transform it to one that doesn't have any epsilon transitions. But you're right. I mean, I haven't done that transformation yet, and I'm not going to do that transformation as a separate step. So you're right that strictly speaking, I should include epsilon here in the domain of the transition function. Yeah. Okay. Thanks. Okay. So I'm going to define the epsilon closure. So the epsilon closure, and so this is a function of a set of states. So I'm going to say the epsilon closure of S of set of states S is the set of states reachable from S by epsilon transitions. Okay. So the idea is that if I have an NFA and I have some states, and I can get from and I have a subset of those states, right? So here S is really a set of states. Then epsilon closure is going to tell me if I start in some state in S, what are all the states that I can get to by following 0 or more epsilon transitions. So the epsilon closure will include S itself, but it might include additional states that, that are reachable from those states. Okay, and so I can use the epsilon closure to transform an NFA by replacing individual states of the NFA with their epsilon closure, or I can use the epsilon closure directly in an algorithm that transforms an NFA to a DFA by every time that algorithm considers a set of states, I would always apply epsilon closure to that set of states to kind of automatically consider all the places that I could get to, also by following epsilon transitions. Okay, so now that I have epsilon closure defined, I can look at sort of the key idea of the NFA to DFA conversion, right? And this is sort of, when you think about it, an NFA seems like way more powerful than a DFA, right? In fact, every DFA is also an instance of an NFA, like a special case of an NFA, but there's so many more NFAs, and NFAs have this, magical oracle power, right? That they sort of automatically predict the right transition to take. So, it's maybe surprising that an NFA can be converted to a DFA. But the key idea here, so the idea is that a set of my, or a state, let's see, so state of my DFA is going to correspond to a set of states of my NFA. Okay, and so that's where we get the magic power. So the idea is that for any subset of or any possible subset of the states of the NFA, we're going to call each subset of the states of the NFA one of the states of a DFA. And that way, the DFA, even though it's only a DFA and it's only deterministic, it can reason about entire sets of states in the NFA. And so this is where the magic comes in, right? Like where how I can get the power of an NFA in a DFA. Okay, and so I'm going to build the DFA out of this key idea, but this is the most important thing. Now when you see this sort of a natural thing to worry about is isn't the DFA going to be really big, right? Because an NFA with n states has 2 to the n possible subsets of states. So if the NFA has n states, the DFA in the worst case could have 2 to the n, exponentially many states. But, the reality is in practice, this never happens or almost never happens unless you have, really pathological NFAs, right? So, yes, in theory, we could have a DFA of exponential size. In practice, for NFAs that we build for compilers, but even for other NFAs, it's very rare for that exponential blow up to be, really exponential. We do get some growth in the number of states typically, but it tends to be tractable. All right, so how do we do this, or how do we use this key idea? So if I all right, so if I call my input NFA is going to be this, right? So my alphabet sigma, my states Q0, A delta, and my output DFA. Well, so the alphabet is the same. So I'm going to use sigma for the alphabet, but now I'm going to call, I'm going to use primes for the other parts of the DFA. So it's going to be Q prime is going to be the set of states. Q0 prime is going to be the start state. And delta prime is going to be the transition function. Whoops. I guess accepting states first. And then, so A prime for accepting states and delta prime for the transition function. Okay, and so to define the transformation, what I need to do is define the primed things in terms of the non-prime things, right? The alphabet is already defined, they're equal, but the other components I have to define. All right, so, I will start with, say, the easy ones. So, what should be U0 prime, right? So what should be the start state of my output DFA? And, remembering the key idea that a state of the DFA is a representation or corresponds to a set of states of the NFA. So, for my start state, I should make it a set of states of the NFA. And initially, the NFA is in the state Q0. So, you might say, well, the start state of the DFA should be a state with it should be a state, yes, a state that's a set of NFA states containing only the start state of the NFA. Okay, and so that makes sense, or that hopefully makes sense, but it's not quite the full definition. What I need to add is the epsilon closure. So I should say the epsilon closure of this set, right? And so that expresses that the NFA, at the very beginning, yes, it's in the start state, but the NFA, after not seeing any symbols yet, could transition to one of the other states in the epsilon closure of the start state. So for the start state of my DFA, I'm going to use the start state of the NFA plus all the states in the NFA that I could reach by epsilons from the start state, right? Because those are all states that I could get to in the NFA without looking at any symbols of the input. And then the DFA, the start state is where I am when I haven't seen any symbols of the input. Okay, so this is, I said earlier, in our conversion of the NFA to a DFA, we're going to use the epsilon closure whenever we have a set. So this is an example of doing that. So ask questions if there's questions here. Okay, so then what? What should I define next? Well, maybe I'll define the transition function. So I'm going to say, so delta prime, so how should I define delta prime of, well, and, its input is a DFA state and an alphabet symbol, right? So Q prime and A. So, and here, Q prime is a representation of a set of NFA states. So, how would I, so what do I do with it, right? So I want my DFA to go to the set of NFA states that the NFA would go to if it started in one of the states in Q prime and saw an A symbol, right, and transitioned on the symbol A. Okay, so, how am I going to do that? Well, I'm going to take the delta function of the transition function of my NFA, and I'm going to run it on all states Q that are in the set Q prime, right? So Q prime is a set of NFA states. So Q is going to range over all the states in Q prime. And I'm going to take the union here, right? So I've got my set of NFA states Q prime. I'm going to look at each of those states, each state in that set. For each one, I'm going to ask the transition function, give me the set of states that the NFA would go to from that state Q on input symbol A. And then I'm going to take the union of those over all of the possible Qs, all of the possible initial states that the NFA could be starting or could be going from on the symbol A. Okay, so this is going to give me a big set of all the states that the NFA could now be in. And so that's going to be, the state in my DFA that I will get to. But again, I want to do the epsilon closure. So, once I get to the NFA could go to any of these states, but then after it has gone to one of these states, it could follow epsilon transitions, and so I want the epsilon closure of this. Okay, so questions there? So wouldn't the epsilon closure be handled by the NFA's transition function? So not necessarily, no. I mean, it would be if you had first done the transformation from an NFA with epsilon transitions to an NFA without epsilon transitions, because there, presumably you would add extra transitions to make up for the epsilon transition. Or another way of saying that, if you had first translated the NFA to one without epsilon transitions, then the epsilon closure would always be the identity, right? Because there wouldn't be any epsilon transitions left. But if the if the NFA has something like this, where there's a state, and then on A you go to this state, and then on epsilon you go to this state, then the transition function from this state on A only has this state in the set, and then from this state on epsilon would have this state in the set. So without the epsilon closure, you would only go here, but with the epsilon closure, you want to go here. Okay, so other questions? Okay. All right, so what is the set of states? And maybe I should have done this one first. Well, so one answer would be the power set of states. So the set of all subsets of Q, right? Could be my set of states. But I mentioned that is exponentially large. So typically when we actually implement this, what we want to do is create these states of the DFA on demand, like as we need them. Okay. And so I'm going to define this as the smallest such that, and I'm going to give some constraints, right? And the constraints are that Q prime has to be a superset of the set Q0 prime, or the set with singleton set with Q0 prime in it. So, in other words, let's see. So Q prime is a set of sets. This should be, I think I need an extra set of brackets here. So yes, so this needs to be in it. And then for all A in the alphabet unioned with epsilon, I want it to be the case that if the DFA can be in a state in Q prime, and the transition function takes me to some other set of states, then that set of states needs to be one of the set of states in Q prime. So the way I'm going to write this is I'm going to say I want the set, so I want Q prime to be a superset of, if I apply delta prime, so if I apply the DFA transition function to some state Q prime that is already in big Q prime, then I want the resulting set of states to also be in Q prime. Okay, so the way I would read this is for every set of NFA states Q prime that is already in big Q prime. So if I already have a DFA state for some set of NFA states, and if I apply the transition function to that Q prime on any A or epsilon, then I want to add the resulting state Q prime to my DFA as well. Okay, and so this, basically is just ensuring that the set of states Q prime is closed under delta prime, right? That whatever state delta prime takes me to, it is going to be a valid state in Q prime. Okay, and then I've got one more, I need to define A prime. So the set of accepting states is going to be the set of all, little Q prime in big Q prime, such that at least one of the states in Q prime is also in A. So, so that the intersection of Q prime and A is not the empty set. All right, so this is saying at least one of the states in Q prime is also in A, and that makes the intersection of Q prime and A not be the empty set. So this definition of A prime is should be mostly straightforward. It's just I'm taking all the states in the DFA, which are sets of states of the NFA, such that at least one of the states of the NFA is an accepting state, and that's sort of the way that acceptance is defined for NFAs in the first place. Okay, so hopefully this one is not confusing. So if there's any questions, do ask questions. And while you're thinking of questions, I'm running out of time. I want to close with an example. And so I want to apply these rules to an example. So I will, let me draw the example, and, you can try to construct the DFA for this NFA. So my example is I have a state 1, and then on a 0 symbol, I go to state 2. And from state 2 on a 1 symbol, I go back to state 2. Then I have a state 3. That's an accepting state. And then I've got the epsilon transition from 1 to 3, an epsilon transition from 3 to 2, and 1. And then I've got state 4, and I've got 0, and 0 going the other way. All right, let me just see. Okay. All right, so that's there's an example NFA. And so at the beginning of next class on Monday, I'm going to go through these rules, applying them to this example, kind of illustrating, I'm not writing out the algorithm, but I'm at least going to show you the algorithm by example. If you're interested, or I encourage you before Monday's class, try to apply these rules to this example on your own, and I'll do it in Monday's class so we can compare to what DFA you came up with on your own. Okay, but the idea is for implementing this Q prime here, if you're going to implement this in your compiler, I would keep a work list data structure that keeps track of all of the new states Q prime, so all the newly added sets of states that you have added to Q prime, but that you haven't processed yet. And then you pull a state off the work list, and processing that state means applying the transition function with all the possible values of A, and adding those states to your work list and to your set of states Q prime. So we will do that on this example on Monday, but you can try it ahead of time to yeah. So I have a question. Yay. So is it possible to pre-compute something small containing Q prime without having to run the NFA? So yes, that's exactly what we want to do. We want to pre-compute all of these, but specifically Q prime, without running the NFA. In a way, what we're doing is we're running the NFA on all possible input symbols to pre-compute Q prime. But in the end, we're going to have, we will have pre-computed Q prime. It will be a set of sets of NFA states, and then each set in that set of sets we will map to, say, an integer. It'll just become a single DFA state, and so we will have pre-computed the DFA entirely without running it on any specific string. And then if we get a string to run it on, we're only running an NFA, a DFA. There's no NFA that we're running when we get a string. So I'm not sure, does that answer the question well enough? Yeah, okay. All right, so I'm over time, so any last questions? Okay, we got a question coming. So let me just... Question? No? Yes? Okay, someone was typing something. All right, I'm going to give 5 more seconds for a question. If you think of questions afterwards, feel free to save them for Monday's class. We will continue, where I left off here. So we'll continue from here on Monday. Okay, so again, a reminder, try to get yourselves into groups. I have about half of you in groups, so try to do that soon. Use Piazza, use Teams, try and get into groups. All right, so have a good rest of the week and a good weekend, and I will see you on Monday.